guys, today we're going to solve a sample problem in chapter 12 of thermodynamics, the heat transfer by radiation. A 3 mm thick glass window transmits 90% of the radiation between wavelength zero point 0.3 and 3.0 micrometer and is essentially opaque for radiation at other wavelengths. Determine the rate of radiation transmitted through a 2 m by 2 m glass window from blackbody sources at 5800 Kelvin and 1000 Kelvin. The given values are thickness is equals to 3 mm and we have 90% of transmitted radiation to the wavelength zero point 0.3 and 3.0 micrometer and the area surface which is 2 meter by 2 meter which is equals to 4 meters squared. For a blackbody source at 5800 Kelvin, the total blackbody radiation emission is equals to the constant proportionality from our Stefan-Boltzmann law times the temperature raised to the power of 4 multiplied to surface area. So plug in the values, we have 5.67 times 10 raised to raised to the power of negative 8 kilowatts per square meter Kelvin raised to the power of 4 multiplied to 5800 Kelvin raised to the power of 4 multiplied to 4 meters squared, which is equals to 2.567 times 10 raised to the power of 5 kilowatts. The fraction of radiation in the range of zero point 0.3 to 3.0 micrometer is fraction of radiation is equals to wavelength at state 1 multiplied to temperature. So plug in the values, we have 0.30 micrometer times 5800 Kelvin is equals to 1740 micrometer Kelvin, which is equals to our fraction of radiation, which is 0.03345. Next, in the state 2, we have fraction of radiation is equals to wavelength at state 2 multiplied to temperature. Then plug in the values, we have 3.0 micrometer multiplied to 5800 Kelvin is equals to 17,400 micrometer Kelvin, which has an equivalent of 0.97875. The fraction of the change of fraction of radiation is equals to fraction of radiation at state 1 minus fraction of radiation at state. Plug in the values, we have 0.97875 minus 0.03345 is equals to 0.9453. Noting that 90% of the total radiation is transmitted through the window. So, the total transmitted radiation is equals to the percentage of transmitted radiation multiplied to change of fraction of radiation multiplied to the total blackbody radiation. Plug in the values, we have 0.90 multiplied to 0.9453 multiplied to 2.567 times 10 raised to the power of 5 kilowatts, which is equals to 2.184 times 10 raised to the power of 5 kilowatts. For the blackbody source at 1000 Kelvin, the total body emissive power is equals to the constant proportionality from Stefan-Boltzmann law times the temperature raised to the power of 4 multiplied to the surface area. Plug in the values, we have 5.67 times 10 raised to the power of negative 8 watts per square meter Kelvin raised to the power of 4 multiplied to 1000 Kelvin raised to the power of 4 multiplied to 4 square meter, which is equals to 226.8 kilowatts. The fraction of radiation in the visible range of 0.3 to 3.0 micrometer is fraction of radiation is equals to wavelength at state 1 multiplied to temperature, then plug in the values we have 0.30 micrometer multiplied to 1000 Kelvin, which is equals to 300 micrometer Kelvin, and which is equivalent to 0.000 as our fraction of radiation. At state 2, we have fraction of radiation is equals to wavelength at state 2 multiplied to temperature. So plug in the values, we have 3.0 micrometer multiplied to 1000 Kelvin is equals to 3000 micrometer Kelvin, which is equivalent to 0.273232 from our table 11-12. So the change of our fraction of radiation, we have fraction of radiation at state 2 minus fraction of radiation at state 1. Then plug in the values, we have 0, 0.273232 minus 0, we have 0.273232 as our change of fraction of radiation. The total transmitted radiation is equals to the percentage of transmitted radiation multiplied to change of fraction of radiation multiplied to total black body radiation. Then plug in the values, we have 0.90 multiplied to 0.273232 multiplied to 226.8 kilowatts. In total, we have 55.8 kilowatts as our total transmitted radiation. So that's all for today, guys. I hope you've learned something. Thank you for watching.